Determination of the concentration of one of the solutions in moles per decimeter cubed and grams per decimeter cubed from the reacting volumes and the known concentration of the other solution. Now, this is effectively a neutralization. Okay, so we're going to be mixing an acid with an alkali and producing a neutral solution. From that, we can then determine how strong the acid was or how strong the alkali was. Okay? So, the first thing I'm going to introduce you to is the burette. Now, this is a bit like a measuring cylinder, but has a higher resolution. So, there are many, many markings between single centimeter cubed. So, we can measure to a finer precision and we can get a higher resolution in our measurements. So, the first thing we're going to do is we're going to wash the burette out, as we do not want any contaminants in the burette that will affect our results. So using distilled water, making sure that your burette is closed, otherwise you will get leakage coming through. So generally having it horizontal means it is closed and there's no liquids that will come out. It's generally good practice to put this down onto the floor. You should never really be pouring chemicals above eye level. You'll notice again I'm wearing my full face goggles. That's because we will be using sodium hydroxide solution, which is an alkali and very, very dangerous. So below eye level, I'm going to, I'll just hold it there, rinse in some distilled water, near enough to the top. Now, once that's filled, I can place that back on the table. Conical flask underneath. Now, when I need to move this, I'm going to unclamp it ever so slightly to move it up. Get my conical flask underneath, and I'm just going to rinse through some distilled water. This will clear out any chemicals in the nozzle and make sure that we get rid of as many contaminants as possible. Close that off, remove the conical flask. I'm just going to give it a little swirl around as well to make sure that I've loosened any solid substances, any particulates that may be in the burette. Unclamp that. And then I'm just going to pour the rest of my distilled water out of the bottom. Making sure to get out as much of the distilled water as possible. This is now ready for use in our titration practical. So, very important we use distilled water and not tap or bottled water, as the ions in the water, dissolved in the water, could affect our results and be a contaminant themselves. Distilled water means we have pure H2O. There is only H2O molecules inside of this water. Now, the first thing we're going to do, we're going to fill acid into our burette. It's generally bad practice to use an alkali because it can be sticky and it can damage the burettes. So generally we will use acids inside of the burette for that reason. Once again, putting it just below my desk onto the floor. I'm going to pour my sulfuric acid into my burette, which is below eye level on the floor. Whoop. Now, you do not need to get this all the way onto 0 because we will be looking at the difference from our starting position and our finish position. It would be very difficult to get that on exactly 0. So to save time, we fill it as close to the top as possible, still keeping on our measurements, and then we'll be taking down the starting measurement, taking down the finish measurement, and that will be the volume of acid that we have added into our titration. Now, once we have filled up our burette, there is a slight air bubble between the valve and the tip of the burette. So we just want to make sure that we have all of those air bubbles through. So now when we start pouring, we're not going to have this air bubble affecting our results. That could be a potential source of error. Burette is fully set up. Now, in your practical booklets, the indicator that you will be using is called methyl orange. Now, I'm going to show you one demonstration with methyl orange, but I'm also going to show you the indicator we will use in lessons, which is phenolphthalein. They will both change colours at slightly different pHs, as you can see from this graph. So the methyl orange changes colour at roughly pH 6, and the phenolphthalein will change at roughly pH 8. Now, they will both show you near enough where they have been neutralised, and we can use either one in our titration calculations. So I'm going to show you one with the methyl orange just to start. In your practical booklets, you will have noticed that it says to use a methyl orange indicator. Now, I'm going to show you what methyl orange will be in an acid and an alkali, but for your practicals in lessons, and for this demonstration, we will be using phenolphthalein, which is another type of indicator. Now, methyl orange So, methyl orange will go red in the presence of an acid, and it will go a yellowish tint in the presence of an alkali, that is pH 6 or above. For the purposes of this, we're going to be using phenolphthalein, but that's just to show you what you would be expecting. Now, for the sodium hydroxide, we will be using a pipette. Now, this is not the same type of pipette you will be used to. This is a much more accurate glass version. Now, for safety reasons and just to simplify things, we won't tend to use the glass ones in class, but I'm going to show you how they are used. Now, you'll notice that just around the top here, there is a line. This is very, very important to get your measurement, get your liquid up to that line. We need to know to as great a degree of accuracy as possible how much solution we have in our conical flask. The one that will vary is the one that we are using to neutralize. Here we have my pipette filler. Now this works just the same way as a normal pipette. You squeeze it and you release it, and when you release, it will suck up any of the fluid that you have placed your pipette into. So very carefully putting my pipette filler on the top, putting it into my sodium hydroxide solution, squeeze it, and as I release, now I have slightly overfilled my pipette. The way I'm going to counter that is if I just gently, I've already gone past it, but just to show you, if I gently release my thumb, that will let some of the liquid back out. Now, using that method, I can get the bottom of my meniscus as close to that line as possible. Make sure you are reading this from eye level so that you can see just where the bottom of the meniscus is touching the line. Releasing very gently, just there. Once you have your fixed volume of solution, carefully transfer it into your conical flask. Making sure to just gently tap off any solution that is still in your pipette. And now we know that we have exactly 25 millilitres of solution in my conical flask to begin the practical with. Place that on the side for now. Now, placing this underneath, take note, again, reading from the bottom of the meniscus, which is the bottom of the curved bit on the top of the burette there. Making sure to read from eye level. So I'm going to tiptoe just enough. So my burette is reading exactly 4 centimeters cubed. So that is my starting volume. So we will go through, and first we're going to do a rough version so we know roughly where our neutralization will occur. Well, I've just realized first I need to add my indicator. So phenolphthalein with a pipette. Add, let's say 5 drops. 1, 2, 3, 4, 5. And you'll see, because it is in an alkali, it's a purple color. Now, we are going to be looking for the moment that it turns completely clear. Here we have my spotting tile that's going to help us identify that neutralization point. We're just using it as a background for comparison. So, starting at 4 centimeters cubed, I'm going to let through big volumes, and every now and then I'm just going to stop, give it a swirl to see if it's changed. Always comparing it to this white tile, swirling every centimetre or so. We want to get this as close as possible. Now, it's very important to swirl as often as you can, because you'll notice that in the middle, where the reactants are just meeting, it is actually clear. But once you, oh, and there we go. So that has now gone past our neutralization point, and it has gone to roughly 17.8. So we know our neutralization point is going to be 17.8 centimeters cubed. So we have added 13.8 centimeters cubed. So that's our rough. That is our rough version. Now, my colleague is going to do another one. He's going to stop maybe about 10 centimeters cubed and add very small increments so that we can get a more accurate result. This is just to give us a rough indication of where that neutralization point was going to be.
Following on from what my colleague says, I'm going to do the precise one. Now, the reason we do a rough one is so I have a rough idea at where the turning point is. By turning point, I mean where it goes from pink to colourless. So roughly, it says here it's 13.8. Now, I know my colleague did it very rough. I'm going to do it much more precisely. Therefore, I'll probably stop, as he mentioned, at round 10 centimetres cubed. After that, I'm then going to literally be adding drop after drop after drop, making sure it is a drop because we want to be so precise in finding that turning point. I'll then show you how we can work out what the concentration of NaOH is, because we know the concentration of this, we know the volume of this, we know the volume of this. Therefore, using our mole calculations and our balanced equation, we can work out the concentration of this. Right, just before, I'm going to add 5 drops into there, and again you'll notice it's gone pink. Okay, that's because it is sodium hydroxide, which is an alkali. I've already filled the burette back up, but in theory you didn't have to. I could have started it where he finished, because I know it's probably going to finish under that, and the burette goes down to 50. So in theory you don't need to top it up after each time. Okay, now the start point of this one is 0.6. Okay, again making sure you're doing the bottom of the meniscus, the bottom of that kind of dip. So start point is 0.6 centimeters cubed. Again, you need to know the start point so you can work out the difference, so we know the exact volume we're adding. Okay, so what you do is I'm going to run it till I get to about 10. Okay. Okay, now I've run it to about 10. It's actually at 10.4 or so. And now I'm going to very carefully add it in. Okay? So making sure you're turning very gently so it is dropping out, because you want the exact point at which it changes. Okay? And after each drop, I'm giving it a quick swirl around. Okay? A quick swirl. Okay? You're trying to be as careful as possible. Now, I know often students aren't this careful, but if you aren't careful, you'll overestimate how much you're adding in. Okay? Now, you'll notice it's nearly all Gone. Right, as you can see, it's now turned, and I've stopped it at the last drop. So therefore, at this level, which is 13.1, remember I'm looking at the bottom of the meniscus, 13.1 centimetres cubed. That is the amount that has changed that known volume of sodium hydroxide. Remember, we don't know the concentration, that's what we want to work out. So this time, therefore, it'll be 12.5 centimetres cubed. Okay? And that's similar to our rough one, but we don't include the rough one at all now. The rough one is just for our own measurement, so I'm just going to rub out the rough because we don't include it. Now, just like every science experiment, or most science experiments, you should do 3 repeats, okay? Now, just for time's sake, I'm just going to leave with this one, but you would do 3 repeats, not including the rough one, and then work out the average. We're not going to do the repeats today because we haven't got as long to do it. So, the volume is 5. Now, before I even start any of the calculations, you're going to have to do the equation. And the important thing is it's a balanced equation. So we have sulfuric acid. And if you don't know, that is the formula for sulfuric acid. We also have sodium hydroxide. Now, the reason this is an acid is because it has H plus ions from there. And the reason this is an alkali is because it has OH minus ions on there. And the cool thing about acids and alkalis is the H plus ions react with the OH minus to form water. It will always form water, which is H2O. The sulfate ion will react with the sodium ion to form sodium sulfate. Now, interestingly, sodium is in group 1, so it's a 1 positive, whereas sulfate is always a 2 minus. So you need 2 sodiums for each sulfate, okay? Now, this is not a balanced equation. So in order to balance it, and you've done this in class, you draw a line down, count how many of each element, and make sure it matches by doing trial and error and putting numbers in the front of them, okay? But I have already worked this out to save time, okay? You need 2 sodium hydroxides for every 1 sulfuric acid in order to get the sodium sulfate, okay? And also, you'll get 2 waters. Remember, the reason it goes neutral is due to the water, okay? Now, the other thing you're going to need to know is the equation, which is moles is equal to concentration multiplied by the volume. Now, I do it in centimetres cubed, therefore I'm going to have to divide it by 1,000, convert it to decimetre cubed. Because actually the equation is concentration times volume in decimetres cubed. But clearly, all my results are in centimetres cubed. So that will be my converting the units to decimetres. Okay? So the first thing I know is, or the first thing I do when I do these equations, is I write down what I already know. And what I know is I know that the concentration of sulfuric acid is 1 molar. Therefore, I'm going to draw 1m. That's quite easy and quite a nice number because that will just go 1 in there. And you know, anything times by 1 is just the same. The volume of sulfuric acid, I know, is 12.5 because that's sulfuric acid is in the burette and that's how far it went down. So I'm going to write 12.5 centimetres cubed. I don't know how many moles there are of sulfuric acid. However, I can work that out through this equation. okay, which I'm going to do right now. I've got concentration is 1, volume is 12.5, divided by 1,000 to convert it to decimeters cubed. So therefore, the moles is 12.5 divided by 1,000, which is 0.0125. Moles, okay? So you've got 0.125 moles. That's how many moles I have of my sulfuric acid, okay? Now, going to the balanced equation, 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide. I don't have 1 mole, I have 0.0125 moles. Just write that on there. Therefore, I'm going to have to double this number, because just like 1, you double 1 mole to get 2, because 1 mole reacts with 2. I haven't got 1, I've got that, but I'm still going to have to double it. So therefore, the moles of sodium hydroxide is equal to 0.0125 times by 2, which is equal to 0.025 moles. Now that's the nice thing about balancing equations, okay? You can clearly see about the number of moles. So 1 mole of sulfuric acid reacts with 2 moles, or if we have 0.0125 moles of sulfuric acid, we have 0.025 moles of sodium hydroxide, okay? Now, working this equation backwards, because we don't know the concentration of sodium hydroxide. However, we do know the volume. So I'm going to write the volume down. Volume of sodium hydroxide, which was 25 centimeters cubed. And we did that by this glass pipette, okay? Because it says 25 centimeters cubed there. So we don't know the concentration, which is what we want to work out. So just plugging it into this equation. Plug it into this equation. We've got X, because we don't know the concentration. We've got the moles being 0.025. We've got the volume being 25 divided by 1,000. Okay, now we don't know what the concentration of this is, but I'm just going to do that divided by that first. So I'm going to rewrite the equation and just do what 25 divided by 1,000 is, which is 0.025. Now, just like with every equation, if you multiply it by 0.025, you have to do the opposite. And whatever you do to one side, you've got to do to the other. So we're going to divide by 0.025 and divide this side by 0.025. Now, as you'll know, that will mean that the concentration will be 1 molar. Therefore, the concentration in this bottle, this sodium hydroxide bottle, is 1 mole, 1 molar. Okay, the concentration is 1 molar, which actually is correct, because it says 1 molar there. But if you didn't know that, this is how we'd work out concentration. And there are plenty of liquids left about with labels torn off, which scientists would want to know the concentration, because too concentrated, well, it could be dangerous and it needs to have certain chemical labels. And not concentrated enough, again, well, we need to know that because it won't react as fast. So scientists do this to try and work out the concentration of different liquids. You find the acid in the burette, you put in your unknown concentration of sodium hydroxide, and then using the balanced equation and the mole calculation for liquids, you can work out the concentration of sodium hydroxide.